Hello everyone, today we will calculate this interesting integral. It is adapted from Putnam competence, and instead of using root square of 2 as in the competence, I use the coefficient, the power 2019. So it's an interesting problem that will deal with our skills for substitution and put some algebra and trigonometry. Okay, here I have used I for the integral. It helps a lot for notation, you will see later. And also I have put tangent of x equal to sine of x divided cosine of x. It helps too for you some properties of sine and cosine. And after this, you will just replace and perform some algebra. That is just to put sine and cosine in terms of 2019 power. Okay, here the idea is to make some algebra for the denominator of the last term of I. So we just perform the algebra and we obtain the expression that appears at first. After this, we use more properties of algebra and cosine that is dividing the denominator passed to the numerator, and then we will obtain the expression shown here in the last part. As you can see, this integral can be attacked using this substitution. So y equal to pi divided 2 minus x. We can do some algebra and put x to the other side and y to the other side and obtain x equal to pi divided 2 minus y. Why the substitution is good in this case? Because, okay, at first, the limits of integration are from 0 to pi divided 2. It tells something. And second, there are two properties of cosine and sine that allow us to use some kind of symmetry that say like cosine of pi divided 2 minus x equal to sine of x, and sine of pi divided 2 minus x is cosine of x. After this, we will replace the value of x in the limits of integration in y. So y in with x equal to 0 is pi divided 2 as shown here, and y where x equal to pi divided 2 is equal to pi divided 2 minus pi divided 2, that is 0. Also, we have to derive the substitution, so dy is equal to minus dx. And these are the important elements that we require to obtain the integral in terms of the substitution. Okay, here we have to remember that we wanted to do this substitution to write I in terms of a new variable that can help us to solve the problem. So the limits of integration will change from 0 to pi divided 2 and from pi divided 2 to 0, because the substitution what that we do previously of I, it showed us this logic. Also, instead of the x, we will write minus dy. And instead of x, we will write pi divided 2 minus I in all the terms. And this expression will be very helpful from now. Also, I have shown a relationship between the minus sign and the integral. And as we can see in the next part, this minus will shift the order of the integral, and it will be very helpful for our expression. So here we do some things. First, we change the order of integration. Now is from 0 to pi divided 2. Also, dy doesn't have the minus sign that had previously, by the reason explained. Additionally, we have put cosine of pi divided 2 minus y and all this term to the 2019 2019. What is the idea? The idea is to see directly what is happening and don't have confusion with the notation. As you can see, the same thing was done with the other parts in the denominator. So all of them follow the same pattern. And we require to make additional algebra to obtain a more simplified version of I in terms of this substitution. So here I put what was the previous expression for I, and after this we remember that in the part where where we put substitution, it was the two properties for cosine and sine of pi divided 2 minus x. It's the same here. Instead of x, just put y, and it works the same. So the numerator becomes from cosine pi divided 2 minus y to sine of y. The power is 2019. And the denominator, the same, cosine of pi divided 2 minus I is equal to sine of I. And we repeat the same with sine of pi divided 2 minus y is equal to cosine of y. And the power is 2019. So this is a neat expression for I in terms of the substitution that we proposed previously. So what is the idea now? The idea now is to add the expressions obtained for y. In this case, you remember that we had previously actually the integral that we obtained was integral from 0 to pi divided 2 of cosine of x at 2019 dx. Okay, as you can see in red. And the black part is the result obtained previously. What happened here? Instead of I put x. Is it a problem? No, it's not a problem because this is just a variable. It doesn't have any mathematical sense by itself. It's just a letter that we put. So we can shift from I to x without any problem. In this case, it works perfectly. And also, they have the same integration limits. So we can add the terms in the integral. As we can see, the terms of the integral have the same denominators, so we can add directly as cosine of 2019x plus sine of 2019x divided by sine of 2019x plus cosine of 2019x by dx. And because both expressions are equal to I, then this sum is equal to 2I. Now this is very interesting because the expression that was inside the integral becomes 1. And you can see it's well defined. Why? Because it's in between 0 and pi divided 2. It's not possible to find a value of x where sine and cosine are equal to 0. So we are not dividing by 0 in any moment, so we don't have problems about a possible singularity in this case. So we can divide without problems, and the expression is equal to 1. So what we obtained that 2I is equal to the integral from 0 to pi divided 2 of the x. And this integral is straightforward. It's equal to x evaluated from 0 to pi divided 2. So 2I is equal to pi divided 2 minus 0. So 2I equal to pi divided 2. We just put the number 2 that is multiplying I, and we divide to the other side. So I is equal to pi divided 4. So our question was to obtain the value of I, basically. And we obtained that I is equal to pi divided 4. It implies that the integral of 0 to pi divided 2 is equal to dx divided by 1 plus tangent of x at 2019 is equal to pi divided 4. So the natural question is, why does it depend on 2019? Or we can put anything here and the result will be the same, or it will change? So as you can see in our solution, the fact of what was the number, if it was 2019 as here, or the square of 2 in the Putnam competence problem, it didn't matter so much. So in both cases, the answer is the same, and actually we can prove that the result is independent of the value that we put over there, and this value is at least a real number. So until now we can say, okay, we have finished this integral. Thanks for watching and keep connected to MATLAB channel.